like ferroelectrics, where you have a permanent electrical dipole that you can switch with a voltage. You can have correlated phases, things like metal insulator transitions, like in V2O3. Oh, okay. Okay, well, okay, there we're back. So you can have things that go from a conductive state to an insulating state under some external stimuli, usually temperature. And you can have things like defect motion, things like oxygen vacancies to create conductive pathways and things like phase change memory. I'm generally going to be focusing on specifically magnetic order as well as ferroelectric order here. Just as kind of a teaser, if we look at this is called an energy delay graph. So this is how much energy it takes to switch a bit, and this is how fast you can switch your bit. So the kind of product of these two is your goodness metric for your device. A lot of projected devices based on functional oxides live in this regime, right? Things like ferroelectric FETs, things like metal insulator systems, things like phase change memory, where modern CMOS, digital CMOS lives here as these pink squares. So these are obviously not in scale production. Otherwise, why would I be talking about this and why would we be researching this? But these are projected to be potentially orders of magnitude better than modern computing schemes for specific applications. For instance, in this case, this is a non-binary kind of neural network architecture. Now, in the semiconductor world, working with thin films is kind of a must. And when I say thin films, I'm talking about things that are tens of nanometers or even less, right? I work with the technique called pulse laser deposition, in which we have a very high energy laser. We ablate kind of a stoichiometric target, kind of just a chunk of material that we're interested in. This superheats the material to the point where it actually creates a plasma, and that the atoms in that plasma adsorb onto a substrate, onto whatever thing we're trying to grow or trying to deposit our thin film. Doing this, we can have control over materials down to the single or double unit cell level. That's a little bit hard to see, but these two unit cells are a different material than it is on the side. Growing materials epitaxially in this way, so you can see the continuation of the unit cell through the atomic columns, and that's what I mean by epitaxial, gives us a lot of games we can play to try to tune the properties of materials as engineers. Specifically, I'm going to talk about this idea called epitaxial strain. So if you have a thin film that you want to deposit that has whatever lattice constant, and you have a substrate that you want to deposit it on that has a little bit smaller lattice constant, your film will be conformed to whatever the lattice constant of your substrate is. And this can create intrinsic strains of up to percents, which is a really valuable technique for tuning the properties in these kinds of thin films. Now, I'm largely going to be talking about materials called ferroelectrics today. And ferroelectrics, if you're not familiar, is a material with a unit cell that is non-centrosymmetric. And this gives it a net polarization. You can see here, this is the kind of canonical barium titanate unit cell, where the center atom, in this case a titanium, is pushed away from the center of the unit cell. It's non-centrosymmetric, and this gives it a polarization. You can think of just like water, right? Water is non-centrosymmetric, and that's what makes it polar. Additionally, for a ferroelectric, I need to be able to apply an electric field, say up in this case, and move this titanium atom from below this middle plane to above this middle plane. I need to be able to switch the ferroelectric polarization. Now, in that case, this barium titanate, which is a canonical ferroelectric, it's a tetragonally distorted and it's relatively simple to understand. I'm going to be talking about almost exclusively today this material called bismuth ferrite, or BFO, BIFEO3. Barium titanate, your center atom is displaced along the 1,0,0 crystallographic direction. In bismuth ferrite is a rhombohedrally distorted perovskite. So the center atom is displaced along the 1,1,1 direction. You can think about a cube if you take the opposite corners and pull it and distort it that way. That's a rhombohedral distortion. But bismuth ferrite is a good ferroelectric, and a lot of people are very interested in it for that. But the reason BFO is so special is because it's also magnetic. And the coexistence of ferroelectricity and magnetism is something that's very rare in materials at room temperature. This is such a desirable kind of combination of properties that people make composites for exactly this purpose. Now, in BFO, not only it's magnetic, it's ferroelectric, but these orders are actually coupled through some of the symmetry relations I'm going to talk about in a second. But this idea of electric field control over magnetism is something that's been very heavily researched for a number of years, at least in kind of DC regime. You can think about doing things like making a magnetic tunnel junction where you have two magnets separated by a tunnel barrier, and you can switch your bottom magnet instead of with a current, like is normally done in modern architectures, but actually with an electric field. Electric fields, currents have a lot of, or dissipate a lot of heat, electric fields don't. And so intrinsically, this is a lot more energy efficient than doing current-based switching events. And so people have been very interested in this from the memory perspective for a number of years. This is all kind of under the assumption, though, that we understand the magnetism and we understand the ferroelectricity of BFO fairly well, which I'm going to argue is not the case. So in BFO, your magnetization and your polarization, I said, are coupled through some of these special symmetries that exist in the material. BFO has what we like to call the pepper grinder mode, which if you imagine your polarization is kind of up-down. If you think about the FeO6 octahedra, so this one right here and this one right here, they're rotated, they're anti-rotated with respect to each other, like a pepper grinder, right? This coupling is actually what allows the magnetization to be switched with polarization. Now, that's great, and that explains a lot of the research that's been previously done, but it's also even more complicated than that. Because BFO is a magnet, but it's not like an icing antiferromagnet that you would normally think about. It's not magnetic moments that are pointed anti-parallel to each other. Because of all these things that are going on in the structure of BFO, the antiferromagnetic moments actually form a long-range spin cycloid that's still antiferromagnetically coupled. So if your polarization is up, and it's in the 1-1-1 direction, you have your 1-1-1 planes that are perpendicular to that or normal to that. These moments are anti-parallel. But then if we move this way, these moments rotate with respect to each other. And so they stay anti-parallel, but they rotate in and out of this 1-1-1. That makes understanding this material a lot more complicated because we can't use some of the early models we were thinking about to explain some of the phenomena that's been done in the past. In this system, because it's the 1-1-1 direction, you have threefold symmetry. And as you would expect, your cycloid can propagate along three potential directions. We have the red one, we have the purple one, and we have the yellow one. These are symmetry equivalent. And if these are the nearest neighbor ions, this direction is the second nearest neighbor ions. If it were an icing system, these would be ferromagnetically coupled. It's even more complicated. So not only do we have the spin cycloid, but which happens because of this pepper grinder mode, the oxygen rotation, the oxygen octahedra, you also have a polarization that creates what's called the Zyloshinsky-Maria interaction, which favors a canting of the magnetic moments orthogonal to this symmetry breaking direction. In this case, orthogonal to the polarization directions. What then happens on top of the cycloid is this DMI actually wants to cant the cycloid out of this plane that's defined by P, which is the polarization, and K, which is the propagation direction. So if this plane is the 1-1-2 bar plane, you have a component that wants to cant in and out of this plane. So as the cycloid cycloids, it wobbles back and forth. And that's very important, and I will talk about it shortly. Now, in real systems, you typically don't get materials that have a single polarization variant. If you have a single polarization or a single magnetization, this creates large stray fields and it's pretty energetically unfavorable. And so your system tends to break up into domains, just like magnets do. The ferroelectric domains in bismuth ferrite, in this case, in the system we're looking at right now, look just like this, where we get a kind of stripe-like domains that point along this 1-0-0 direction. And this domain pattern comes from the epitaxial strain that's induced by the substrate. So the substrate we deposit this material on is called dysprosium scandate. DSO gives it about a 0.5% compressive strain onto the film, so it squeezes the film a little bit. And it's a little bit anisotropic, which creates the preferred direction for these domain modes. Now, these domains are what we call 71-degree ferroelectric domains. We call them that because if we have this kind of up, back, right polarization and this up, front, right polarization, the angle between these is 71 degrees, so 71-degree domain wall. And if you look at the in-plane projection of these domains, it kind of zigzags back and forth as you go through it, right? So the black domain is up and then right and then up, right, up, right, up, right, up, right. And it kind of zigzags back and forth. Now, as I've been saying, the magnetism is very strongly coupled to the polarization in BFO. And so if the polarization is doing this zigzagging back and forth, we might also expect the magnetism to do something like zigzagging back and forth. I guess now I can't change the slide. Okay, we'll do this. That's fine. If we go and measure it, it turns out that this is true. So if we have a magnetic cycloid in BFO, the magnetic cycloid looks like a plane wave. When our polarization is up, the cycloid goes to the right and to the left. It's like a plane wave propagating this way. Our polarization is to the right, our cycloid looks like a plane wave propagating up and down. Now, this ability to measure the magnetic, and this period is about 60 nanometers. Now, this ability to measure the magnetic cycloid in BFO directly is, I think, some of the coolest parts of the modern research that we're doing. Right? This technique has only been around a couple of years. And I said earlier I was going to shout out Paul, and because this is the technique that I'm doing with Paul. These measurements are actually done here, right? The way we do this is with a what's called a scanning NV magnetometer. And so we have a single crystalline diamond scanning probe tip, so we can do spatial mapping. And an NV center acts like kind of like a trapped ion or an individual ion, which makes it very sensitive to Zeeman splitting from very small magnetic fields. If we look at that splitting as a function of space, because we're in a scanning probe technique, that allows us to map out these very, very small magnetic fields of 1 to 2 Ørsted at the surface. And that's really what enables this technique. Now, what we're doing is we're mapping stray magnetic fields, and the cycloid itself should have a very small magnetic field. That's why I wanted to bring attention to this spin density wave component, this out of plane canting of the cycloid, because this is actually what we're measuring in this case. Now, this happens because as our polarization changes, if we draw our purple, our red, our yellow propagation vectors of the cycloid, so we go across our 71-degree ferroelectric domain wall, you can see that all of these propagation vectors are different, right? The yellow changes by 90 degrees, this one changes by 90 degrees. And if we map that on a large scale and we kind of overlay it on the ferroelectric domains, we get something that looks like this, where wherever we have a black domain, which is the polarization pointed up, we get a cycloid that cycloids this way to the right and the left. When we have an orange domain to the right, we get a cycloid that cycloids up and down, right? And these domain walls exactly match up with our ferroelectric domains. Even where we have these little defects, like we see right here, we get a continuous rotation of the cycloid in BFO. Now, one thing we also see is that even though there are these 3 symmetry allowed directions of the propagation vector, we only ever see this yellow, right? If our crystallographic directions or cardinal directions are on the diagonals, we only ever see the up, down, and the right, left. We only ever see this yellow. And the question then is why? Well, as a thin film person, we can hypothesize that is due to strain. We know we're straining our thin film, but this interaction between magnetoelasticity and this kind of complex magnetic texture is not necessarily physics that's either well understood or can even be guessed. So one thing we can do to try to understand the physics a little bit better is we can go to first principles. Now, in general, the cycloid in BFO is very, very difficult to do with density functional theory. The period of the cycloid is 65 nanometers. That's 200 unit cells. If you want a cube, that's something like 10 to the 4 atoms in your supercell, and that's effectively unachievable using something like density functional theory. What we can do though, or what we think we can do with modern DFT functionals is we can break this up into manageable chunks. We can create supercells that are effectively icing system, but a single chunk of the cycloid, and then rotate it through this angle L of phi. And we can try to understand some of the physics of the system. Now, we think this is right, and we think we can do this because we've done I think a good amount of control experiments. If we try to put the cycloid exists in the 112 bar plane, the polarization along the 111. If we try to rotate these spins in another plane, we get much higher energy values. So we can recover the generally understood definition of the cycloid from doing it in this way. So that's great. Additionally, I mentioned this spin density wave comes out of the DMI that comes from the system of the global interaction between the magnetization and the polarization. It's not necessarily a unit cell level thing. It's closer to a thermodynamic effect. And using our kind of doing the DFT in this way, using the modern functionals, we can naturally recover the spin density wave component from breaking up the cycloid like this, and it has the same period of the cycloid with the same, I guess, sense or the same chirality that we would expect from the phenomenological model. So this all checks out, and it seems like we can come up with a pretty good definition of the cycloid using density functional theory. Now, the more interesting question is, why does our cycloid only select those the yellow directions in our experimental sample? If we do the same experiment and we constrain our unit cell in biaxially, so in plane to the lattice constants of the substrate, we recover a very clear anisotropy that favors the yellow cycloid direction, which is good and agrees with our experiment and somewhat intuitive. But this allows us to potentially ask the more interesting question, because the magnetization is not just coupled to the polarization in the ground state. In fact, ferroelectrics are interesting because you can switch them with an electric field. So what happens to the magnetization as we switch it with an electric field? In bismuth ferrite, when we have our kind of stripe-like domains, if we just put down in-plane electrodes or in-plane text structure, so we can apply an in-plane this DC electric field along this direction. We can make our nice ferroelectric hysteresis loop as we switch it back to the left and to the right. And on the unit cell level, this corresponds to what's called a 71-degree ferroelectric switch. So you switch from the black arrow when I have a field pointing to the right, to the gray arrow when I have a field pointed to the left. And each of these domains will do this kind of switch individually. And this is a somewhat well-known thing to do, a well-known way to switch PFO. If we look at the in V data, as you might expect, when we have our black domain, so in this case it's bottom left, we get a cycloid that cycloids along this diagonal. When it's up and to the left, we get a cycloid along this diagonal. But when we have a net polarization pointed this way, because we're zigzagging this way, but when we switch it, when we look at the black domains, which are down to the left, and the white domains, which are up and to the right, use the anti-parallel polarizations, but K is an axis. K is not a vector. So you get the same cycloid in the white domains as we do in the black domains, or observably the same cycloid. We get a cycloid that goes, where's a good image? Right here. We get a cycloid where the K vector is this direction. So again, this is maybe not the most unexpected thing in the world. If we're doing a 90-degree rotation of the polarization, we would expect a 90-degree rotation of the magnetization. And this kind of obeys all the same symmetries and the anisotropies that we were just talking about. We can also, because we can do this in the tool, we can also look at this functionality a little bit more dynamically. So we can have our device, and we can also land the scanning probe tip in between the device. So we can apply an electric field and measure the magnetic texture while we're applying an electric field. So if we sit at one point, and of course these are illustrations, but if we look at the middle domain where it's negative voltage, we have a polarization up, and we slide the cycloid this way. When polarization to the right, the cycloid switches, and then that same domain, when we go back to the negative field, the cycloid returns to approximately the same as the first state. And so this is reversible. It's a 90-degree rotation as we rotate P by 90 degrees. And all this checks out as far as the symmetry. The more interesting question, though, happens when we talk about out-of-plane electric fields. So if the film is the plane of the floor, we're first applying electric field this way, which should be all symmetry allowed and should all check out. But if we apply an electric field in the up-down direction, things are more complex, as is everything with bismuth ferrite. We can do this by using a conductive tip in our scanning probe system. And if we ground a back electrode and apply a voltage through a conductive tip, we can write polarization domains in the ferroelectric material. But bismuth ferrite, when you switch it in this way, when you apply an up-down electric field, it doesn't just go from this to this, right? It's a lot more complicated than that. And there's been a large amount of very good research on this. But bismuth ferrite, when you apply an up-down electric field, it'll go through complex switching pathways and very often end up with a polarization that's 180 degrees from where you started. I say this is more interesting because in terms of the magnetic structure, now we have to think about these anisotropies we're introducing through the magnetoelasticity. So we can do this experiment. And so this is a map of the ferroelectric domains, the same as before, but this is actually vectorized. And so we'll say the white domain is in the 111 bar direction. And we can do this by, if we measure our as deposited state, and then we use the scheme with our scanning probe tip to switch a large, about a 10 micron area with +8 volts. So this is a net out of plane polarization down. The dark area is a net out of plane polarization up. And then we can go in the center and we can switch it back down again. So we can go through 1 or 2 out of plane switching events. The reason we do this and we vectorize it in this way is because we can then calculate what the difference between the starting and the ending polarization is, right? So the yellow is anti-parallel starting and ending configurations. The light green is 109 degrees, et cetera, et cetera. If we then go and measure the magnetic data with the NV microscope, we can see that with an area that's switched once and the area that's switched twice, even when it goes through these complex switching events, for instance, a polarization that's 180 degrees from the starting state, we have a polarization that's down and to the left, and we end up with a K vector that's up and to the right, or that's along this diagonal. It appears that regardless of the switching pathway, regardless of how complex it is and the multi-step switching pathway, the magnetic cycloid finds a ground state that satisfies the symmetry with the final polarization state. Now, again, we know the anisotropy exists, and so this is not the most complex thing in the world. If we talk about our symmetry operations that we have to go from this state to this state, that is just the symmetry definition of anisotropy. You have to go through the lower symmetry operations to end up in a state that's acceptable to your energy landscape. But we can start, it shows that even applying this large strain to the system, this large energy term, we still have the cycloid. We're not breaking the cycloid down into an icing like antiferromagnet, which is what some people thought would happen. But also we can think about engineering the material now to fit the kind of device that we want to optimize spin transport. I mean, specifically, when I say spin transport, I'm specifically talking about spin waves. I'm talking about magnets. Now, this is all done with dysprosium scandate as the substrate, which is about a 0.5% compressive strain. It squeezes the film quite a bit. We can also think about terbium scandate, which is the same symmetry substrate, but with a much lesser strain state. It's almost a neutral strain state. So we don't have that very large magnetoelastic anisotropy that we did in the DSO. You can see that in the diffraction, where this is the DSO. The substrate peak is far away from the film peak. And in this case, the substrate peak is close to the film peak. That just means there's less strain in this case. The other difference, though, is that when we deposit our samples on the terbium scandate, we get a very different domain configuration. So if you remember before, we had our so-called 71-degree ferroelectric domains. These domains are big. These domains are like 300 to 500 nanometers. But in the case of the terbium scandate, we get what we call 109-degree ferroelectric domains, which 71 degrees was the difference between this and this. 109 degrees is the difference between this and this, right? It's just the difference, the angle between the starting and the ending polarization states. It zigzags through the same way, orthogonal to the domain walls, but they have different out-of-plane components. Additionally, these domains are much, much smaller than they were on the dysprosium scan date. Or they were about 200 to 500 nanometers. These are about 20 to 30 nanometers. This is even smaller than the period of the magnetic cycloid. And so if we're thinking about the difference then, in our 71-degree domains, when we change our polarization state, all of our selected K vectors are different, right? We have the purple, the red, and the yellow all change between two states across the domain wall. In the 109-degree domain wall, the purple propagation vector doesn't have to change because it's orthogonal to both polarization states. And thus we might expect, well, if this is the symmetry favors cycloid propagation, is that what we see in the system, and that it doesn't have to change across ferroelectric domain walls? That is exactly the case. It's almost like I'm setting up my own explanation. But if we look at our sample on the dysprosium scan date, where we have this nice zigzag pattern, and these are in the same crystallographic orientation, where our K vector is along 110. On terbium scan date, we have a wider period cycloid, which comes from the projection. But it points along the 100 direction, which, because of the projection, we know is the 101, the purple K vector, because that's the symmetry allowed one. But also, we only get a single variant of the cycloid, and it doesn't do anything at the magnetic or at the ferroelectric domain wall. So this domain is 500, 700 nanometers wide. There's a lot of ferroelectric domain walls inside of it. There we go. If we look at this on a larger scale, we still see an approximately single variant of the cycloid. We zoom in, we have lots of ferroelectric domain walls that go through ostensibly continuous, I'm going to call them tubes or parts of the plane. On the other hand, though, you can clearly see all these almost antiphase boundaries that happen in the cycloid. In these 109-degree domains, we should stay on this slide for a second. These domains are very fine, but they have a net, but when they zigzag this way, they have a net polarization that's pointed to the right? Globally, you can have families of these domains or macro domains where you have a zigzag with a net polarization that's pointed to the right and a different macro domain with a zigzag where the polarization is pointed to the left. Still 109-degree domains, but instead of this configuration, you have the exact mirror of this, where it's up and to the left and it's down and to the right. These boundaries match up pretty perfectly with the antiphase boundaries that we see in the magnetic cycloid. And we think that this is due to the actual chirality and the sense of the magnetic cycloid in the structure. So cycloids, by definition, are achiral structures, right? They are mirror symmetric. But because of this canting of the cycloid outside of the 112 bar plane, it actually takes on a sense, and it takes on a chirality, which doesn't change, and thus it's dependent on the polarization. So if I have a net polarization pointing this way, I have a chirality that spirals clockwise. If I have a net polarization pointing this way, I have a chirality that's still clockwise, but has the opposite sense when viewed from the top. These are and that gives you a pi out of phase. These, we think, are these antiphase boundaries that happen in this system. Now, also that we have a single variant of the magnetic cycloid, we can start to think about what happens when we try to pump spins along the two different directions of the cycle, right? This is cool physics, but it has to be actually useful for something, right? And this is what we want to think about the perspective we want to think about these structures from is how can we optimize spin transport in the material? The way we do this has existed for a number of years in the spintronics community, but what we can do is have two wires, one of a material with a large spin Hall angle, which will convert spin current, so a preference for one direction of spin, into a voltage differential. In one wire, we can thermally excite spin waves, which then either travel the length of the device or get excited somewhere within the device because of the thermal gradient. this creates a spin gradient, which is a spin current, and that gives us some kind of voltage differential that we can measure at the detector side. Now, thermal effects are somewhat messy physics, but we're relatively confident that this is what's going on, and this is the process that's happening. So, naively, just looking at the structure, you might expect that if you try to do transport in the up-down direction, that's with the propagation vector of the cycloid, that's the cosine-like behavior of the spins, that's hard, right? You have a lot of rotating spins. And if you try to do it in this direction, which is where all the spins are ferromagnetically coupled, that might be easier, because if you think about a magnon in a simple system, you have Ising spins that precess, and that wavefront moves along, and well, this direction locally looks like a ferromagnet. It turns out if we do the experiment, we see that pumping spins this way along the 1, 0, 0 direction is comparatively hard to pumping spins along the 0, 1, 0 direction, or exciting spin waves along the 0, 1, 0 direction. And this is by about a factor of 4, right? So easy in the ferromagnetic direction, hard in the cycloid direction. We can compare that to in the other sample where we have a nice zigzag pattern, where when we excite a magnon this direction, the up-down direction versus the left-right direction, we don't see this anisotropy. They sit right about on top of each other, which is, again, in kind of a toy model sense, what we might expect, right? We have no net propagation of the cycloid in this case, and so we would expect no net anisotropy. Additionally, and I think this is a cool observation if it's true, but we're not totally confident that it's true, that if we pump spin this way, it's hard, we get a low value. If we push magnons to the right and the left, it's easy and we get a high value. If we push magnons along the 45 degrees, well, we would expect something that looks like √2 between hard and easy, and that's about the value that we see. So I think if that's true, that's pretty neat. But that's not a very quantitative picture. We'd like to be a little more scientific about it, and so we can look at phase field and as well as first principles. If we simulate and we create a structure that just looks like a simple ferromagnetic cycloid, so this is not a perfect representation, but I think to some degree illustrates what we wanted to illustrate. If we try to push a spin wave along the direction of the cycloid, so along the cosine-like direction, we don't really see any excitation. Our initial state and our equilibrium state are almost indistinguishable, which means there's not really anything going on. If we do the opposite and we try to push a magnon along the ferromagnetically coupled direction, it looks like what you would expect out of a spin wave. This amplitude is scaled up just so we can see it, but we have Ising-like spins that are processing in the way we would expect it to. And so by then engineering the direction of the cycloid, we can tune potentially the magnon transport in this material, which is something that we're very excited about, because again, the structure can also then be switched with an electric field. And so if we could tune from easy transport to hard transport by applying electric fields along different directions, that is a spin pump, and that's a pretty cool physical concept. All right, I do want to somewhat briefly touch on that actual electric field control over the spin transport, because that's why we're doing this. We want to make a useful device out of this system. And it turns out that if we optimize our detector wire to be a material with a very high spin Hall angle, something higher than platinum, something like strontium iridate, which has a debatably high spin Hall angle of greater than 1. Doing these switching experiments, we can actually reach non-local voltages of tens to hundreds of microvolts to millivolts. And that level of voltage is almost enough to do something exciting with. That's almost enough to switch another device, if you wanted to create something that cascades between devices. Because if we want to do computation, ultimately that's what we need. We need an output that can then change the input of the next system. This switching also happens because of, we think, the chirality of the cycloid. So if we have our zigzags to the left and we have our zigzags to the right, that ostensibly looks like the same magnetic texture when viewed from the top. But because we have this DMI that's tied to the polarization, this gives us what we think is a different density of states that's coupled to the polarization through electromagnon is a loaded word, but I'm going to say it now. We have a density of states of magnons that's coupled directly to the polarization direction through the chirality of the system. And that's something we're very excited about moving forward. So with that, I'm going to end, I guess, 4 minutes early. And I'll throw up this pretty picture as well as some of our works that we're submitting and working on, and I'd be happy to take any questions.
Try the first one.
Yeah.
Very, very nice. I like it. I remember earlier years when we had like 7, 8 years ago, had a joint input programs. So we did some sample image used. Those sample image doesn't really have this kind of fine features.
Yeah, absolutely.
It's like most of the domains are kind of like imprinted by the polarization.
Right.
Beneath.
Yeah.
And then we see like antiferromagnetic domains, but really we have no idea of this kind of fine features. So I was just wondering, I mean, supposedly we could use like AFM, conventional, just use magnetic instead of using infer, for example. We could. Is there any work done on that? Similar?
It is. So in intrinsic BFO, it's, I don't want to say you can't, but no one's been able to do it because the fields are just so small. In some of these doped BFO concentrations, like the 20% cobalt doped BFO, which has a pretty weak ferromagnetic moment, you can kind of see it with MFM, but it's right on the borderline. Yeah, absolutely.
I was the former, but it's very impressive.
Yeah. In fact, this one is so this is with Masaki Asuma's group, and they specifically did it with MFM, and then we took it and did the NV at the same location to show that their MFM is reasonable.
I have some questions about spin waves.
Okay.
So I guess maybe you can help me think about the right way to just think about the spin wave propagation with the cycloid texture, because we can have spin waves that have different spatial frequencies.
Yeah.
So is this going to be the case that you're essentially only allowed to, or you can only generate and excite spin waves that have a spatial frequency that matches that of the cycloid underneath, or like how does that?
That's a good question that I don't think I'll give you a satisfying answer to. Our thoughts are that when you go, if I go back, when you go this direction, so when you go in the ferromagnetic looking direction, your dispersion is going to look a lot like a ferromagnet. But in the other direction, we've never been able to calculate anything reasonable that shows there is actually a mode we can excite outside of the actual like vibrational mode of the structure.
You can have in just like a regular ferromagnet spin waves that look like this.
Yeah.
And you can even just break it down into, is it the direction of propagation that has the higher spatial frequency? So as I'm wondering, is that the right way to think about this, or does the underlying, the fact that we're not starting with everything pointing in the same direction, have that underlying landscape?
Sure.
In that description of what could be said.
Yeah, it's a good question. Because so in these simulations, we have to impose such a high anisotropy to actually get the ground state that the actual frequencies we get are not anything reasonable. Is it, I think, yeah, I think kind of the conclusion we've come to with the kind of the folks doing the simulation, as well as some folks doing some analytical calculations, is that in this direction, it looks a lot like a ferromagnet. You have a very normal looking dispersion, even though you have, you know, kind of all your directions of your spin moving this direction, everything's ferromagnetically coupled. Again, we haven't calculated a dispersion that we think is reasonable for moving in the other direction.
Do we have any questions from the online audience? Please raise your hand or unmute yourself.
Yeah. It'll take me a minute, but yeah, the other direction.
Texture. I'm just curious where those limits come from.
So like this guy, these guys right here.
Which you don't see in the concentration vector.
Yeah, so there's one that's like right about here, and that's what frustrates the structure right here. And then there's another one that's kind of right here. So you do, and there's one right here. So if you know where to look, you can kind of pick them out. They very likely come from just like either mechanical or crystallographic defects in the film. Yeah, absolutely. So it's when your structure is very nice and perfect, you get kind of this stripe-like domain pattern. But as you start to frustrate it and move away from the anisotropy of the substrate, it'll break up into what we call 4-variant textures, which here, this is kind of what's starting to happen. So you get, yeah. Yeah.
And you know, devices like that sort of limited by how quickly you can change those. Do you have a sense of like what time scales?
Yeah. So the time scales of materials like BFO are limited by the ferroelectric switching, which is time scales that are like picoseconds, right? So not super fast in terms of things. There's a lot of engineering work that's gone into kind of the composition of this material to make it switch faster, switch at lower fields. And conceivably you could do some kind of things if you wanted to engineer an actually good device. But I think for showcasing just the physics, this works for now. Yeah, people definitely try to do it. There's a lot of work actually that's gone into like photoferroelectric effects in BFO because the band gap's pretty small. But it's 2.5. Yeah. So it's not semiconductor small, but like small for an oxide. There people have done it with like terahertz pulsed stuff to try to actually switch it, but I don't know of any work that's been done outside of like synchrotron experiments.
So
Yes, yeah. I think somebody's got a raised hand.
Hi. Very nice talk.
Can you please ask your question? Yeah.
Yeah. In the earlier page, one page earlier, last slides, distance dependent spin simultaneous transport, magnetic transport. Yeah. In the middle figure, so on the left side of the point, is it the experiment point or is a calculation or simulation? Because see, it's the spacing seems to be very small at scale. Not sure if hello,
Yeah.
can you hear me?
Yeah, I understand. So yeah, so this is experiment. The different colors in these points are different device schemes. So the kind of non-local transport I was talking about are the red and the blue. These other colors, specifically the ones that are really small, are not lateral devices, but vertically integrated devices. So the thickness here is actually the thickness of the thin film, exciting from a bottom electrode and then reading from a top electrode.
Oh, got it. Thank you.
All right. Yeah, other questions? Let's take the speaker one time.
Thanks, everyone.
Thank you, everyone. See you next week.